Every deep image the James Webb Space Telescope has produced contains the same uninvited guests. Tiny, crimson points of light, scattered through the background like flecks of rust on black glass, showing up in nearly every long exposure the telescope has ever taken. Nobody asked for them. No model predicted them. And for nearly 4 years, nobody could fully explain what they were. That changed only weeks ago, when a single object behind a galaxy cluster handed astronomers the clearest picture yet of what these objects actually are. The answer involves black holes, but not the kind most people picture. It involves a strange evolutionary stage in cosmic history that may only have existed for about 1 billion years, sometime near the dawn of the universe, and it touches almost every major open question in modern astrophysics. From how galaxies formed to whether our standard model of the cosmos itself needed fixing. Before getting to the answer, it helps to understand why this puzzle existed at all, and why solving it took so long. In 1995, the Hubble Space Telescope pointed at a patch of sky that looked, to the naked eye, like nothing. No bright stars, no visible galaxies, just a tiny black square chosen specifically because it appeared empty. Astronomers called this kind of observation a deep field. The idea was simple. Point the telescope at one spot, hold it there for days, and let faint, distant light accumulate pixel by pixel until something becomes visible. When the image finally came back, that empty patch of sky was packed with thousands of galaxies, some of them among the most distant objects ever recorded at the time. The Hubble Deep Field became one of the defining images in the history of astronomy. Proof that darkness, examined long enough, is rarely actually dark. The James Webb Space Telescope, launched on Christmas Day in 2021 and fully operational by the middle of 2022, was built in part to repeat that experiment, but with far greater sensitivity and at much longer wavelengths. Webb sees primarily in the infrared, which matters enormously for looking deep into the universe's past. As the universe expands, light traveling across it gets stretched, shifted from shorter, bluer wavelengths toward longer, redder ones. Astronomers call this redshift. The more distant and ancient the light, the more extreme the shift, until visible light emitted billions of years ago arrives at Earth as infrared. Hubble could see fairly far back. Webb was designed to see much, much farther, deep enough to glimpse the era when the first galaxies were assembling out of raw gas left over from the Big Bang. When Webb's own deep field images started arriving in the summer of 2022, astronomers expected a sharper, deeper version of what Hubble had already shown them. More galaxies, more structure, more confirmation of existing models. What they got included that, but it also included something nobody had requested. Scattered across nearly every image, sitting between galaxies, sometimes overlapping them, were small, point-like sources glowing distinctly red. They had no visible spiral arms, no extended structure, nothing that looked like a normal galaxy. They were just dots, compact, faint, and a shade of red that stood out clearly once researchers started looking for it. At first, some teams assumed these dots were artifacts, instrument noise, or contamination from cosmic rays striking the detector. That explanation collapsed almost immediately. The dots appeared consistently across multiple independent surveys, observed by different teams using different instrument modes in different patches of sky. Whatever they were real, and they were everywhere. By late 2022 and into 2023, researchers studying Webb's Sears survey, its JWST survey, and several others all began reporting the same population of objects, eventually converging on a shared name, little red dots, a description rather than a technical classification, because nobody yet knew what technical category they belonged to. The numbers kept climbing as more data came in. By 2024, hundreds of these objects had been catalogued across Webb's various deep surveys. By 2025, the count had reached roughly 341 confirmed little red dots. And that figure represented only the objects bright enough and well measured enough to make a formal catalogue. A small fraction of how many likely exist within Webb's full field of view. For comparison, that means in essentially every direction Webb has looked deeply enough, it has found them. They are not a rare anomaly tucked into one unusual patch of sky. They are a fundamental feature of the early universe that earlier telescopes were simply never sensitive enough to detect. The redshift of these objects placed them at a specific narrow window in cosmic history. The little red dots begin appearing in large numbers starting around 600 million years after the Big Bang, and they become essentially absent from the population. By roughly 1.6 billion years after the Big Bang, outside that 1 billion year window, they are rare or entirely missing. Something about the conditions of the very early universe allowed them to form in great numbers, and something about the universe's continued evolution caused them to stop forming, or to transform into something else, within that relatively narrow slice of cosmic time. To put that timing in perspective, the universe today is about 13,800 million years old. The little red dots existed and then vanished within the first 2 billion years of that timeline, while the cosmos was still extremely young, still assembling its first generations of galaxies, still working out the basic architecture that would eventually produce stars, planets, and eventually the conditions for life. Finding a population of objects this consistent, this widespread, and this tightly confined to one early era told astronomers they were looking at something tied directly to the physics of galaxy and black hole formation in the infant universe, not some peripheral curiosity. The next step was figuring out what these dots actually were made of, and that required spectroscopy, splitting their light apart by wavelength, to read the chemical and physical fingerprints embedded in it. What came back was, in its own way, even stranger than the dot's mere existence. When astronomers split the light from a little red dot into a spectrum, two features stood out immediately. First, the overall shape of the light curve was unusual. In the ultraviolet and blue part of the spectrum, the light was relatively faint. Then, moving toward the optical and into the infrared, the brightness rose sharply, producing a shape researchers started calling a V-shaped continuum, faint blue light, climbing rapidly into bright red and infrared light. Ordinary galaxies full of stars do not typically produce that shape. Normal star-forming galaxies tend to have smoother, more gradual spectra, because starlight comes from a wide range of stellar temperatures blending together. A sharp V-shape suggested something else was contributing extra light specifically in the red part of the spectrum, on top of whatever stars might be present. Second, many of these objects showed broad emission lines, particularly from hydrogen. An emission line is a spike in brightness at a very specific wavelength, produced when atoms absorb and then re-emit light at characteristic energies. A narrow emission line means the emitting gas is moving slowly and uniformly. A broad emission line means the gas producing it is moving at a wide range of velocities relative to the observer, smearing the spike out across a range of wavelengths through the Doppler effect, the same phenomenon that changes the pitch of a passing ambulance siren. The hydrogen lines coming from little red dots were broad, often astonishingly so, implying gas velocities of several thousand kilometers per second. To put that into a more tangible comparison, gas moving at roughly 2,000 kilometers per second could cross the distance between Earth and the Moon, a span of roughly 384,000 kilometers, in well under 4 minutes. broad hydrogen emission lines moving at speeds like that are a textbook signature of one specific kind of object, an active galactic nucleus, often abbreviated as an AGN. An active galactic nucleus is what astronomers call the central region of a galaxy when a supermassive black hole there is actively pulling in surrounding gas and dust. As that material spirals inward, friction and gravitational compression heat it to extreme temperatures, and the resulting accretion disk radiates enormous amounts of energy, often outshining every star in the galaxy combined. The broad line region around such a black hole consists of gas clouds orbiting at high velocity close to the black hole's gravitational influence, and the line widths trace those velocities directly. The broad hydrogen lines in little red dots looked exactly like what astronomers expect from this broad line region. That single clue reframed the entire mystery. If little red dots were not just unusual galaxies, but galaxies hosting, actively feeding supermassive black holes, then Webb had stumbled onto an enormous population of black holes that existed far earlier in cosmic history than almost anyone expected, and in far greater numbers. That conclusion came with an immediate complication, because everything else about these objects refused to behave the way an ordinary active galactic nucleus should. The first complication was X-ray emission. Active galactic nuclei are reliable X-ray sources. The inner accretion disk around a feeding supermassive black hole reaches temperatures of millions of degrees, hot enough to radiate strongly in X-rays, and this X-ray signature is one of the most dependable ways astronomers confirm a black hole is actively accreting. When researchers pointed the Chandra X-ray Observatory and stacked deep X-ray exposures at the positions of known little red dots, the X-ray signal was almost entirely absent. Individually, almost none of them showed detectable X-ray. Even stacking dozens of them together, combining their faint signals to search for a hidden average detection, produced barely a trace. A population of supposedly active, feeding black holes that produces essentially no X-rays is, by the standards of everything astronomers thought they understood about accretion physics, a contradiction. The second complication concerned mass. To estimate the mass of the black hole sitting inside a little red dot, astronomers used the width of the broad hydrogen lines combined with the object's luminosity, a long-established technique used throughout extragalactic astronomy. The masses that came out of those calculations were enormous relative to the apparent size of the host galaxy. In the modern, nearby universe, supermassive black holes and their host galaxies follow a tight relationship. More massive galaxies host more massive central black holes, in a ratio that stays fairly consistent across thousands of measured systems, a relationship astronomers call the M-sigma relation. The little red dots broke that relationship badly. Their black holes appeared to make up a far larger fraction of the total system mass than the relation allows, in some cases implying a black hole containing several percent of the entire galaxy's stellar mass, compared to a typical modern fraction closer to 1/10%. Worse, several of the host galaxies implied by these measurements were astonishingly small and compact, in some cases packed into a volume of space comparable to or smaller than our own solar system, yet radiating with the combined output of roughly 250 billion suns. That combination, an enormous black hole crammed into a tiny galaxy, producing immense luminosity with no measurable X-ray, sitting at a cosmic epoch when the universe had barely had time to form its first generation of galaxies, did not fit comfortably into any existing framework. It is worth pausing on just how much energy is implied by 250 billion suns of luminosity. The sun itself outputs roughly 380 quadrillion watts of power, written by scientists as 3.8 times 10 to the 26th watts. Multiply that single star's output by 250 billion, and the resulting number describes the energy radiating from a region of space that, in some of these objects, could fit comfortably between Earth and the outer planets of our own solar system. Faced with a population of objects that seemed to violate several independent lines of established physics at once, researchers spent the better part of 2 years testing every reasonable explanation they could construct, and watching most of them fail. The first candidate explanation treated little red dots as ordinary, if unusually compact star-forming galaxies wrapped in thick layers of dust. Dust grains absorb blue and ultraviolet light efficiently, while letting redder light pass through more easily, which can produce a reddened spectrum without invoking a black hole at all. This explanation had one major strength. Dust is common, well understood, and does not require inventing new physics. It had several weaknesses that proved difficult to overcome. Heavily dust-obscured starburst galaxies still tend to glow brightly in the mid-infrared, because the dust itself absorbs starlight and re-radiates that energy as heat. Little red dots largely did not show that expected mid-infrared glow. Their broad hydrogen emission lines also remained difficult to explain through star formation alone, since ordinary star-forming regions do not typically produce gas moving at several thousand kilometers per second. Dust could explain the color. It struggled to explain the motion. A second candidate explanation kept the active galactic nucleus interpretation, but proposed that ordinary interstellar dust within the host galaxy, rather than anything unusual about the black hole itself, was reddening the light and blocking the X-ray. Dust is, after all, known to absorb X-rays effectively when present in large enough quantities along the line of sight. This explanation faced its own problem: the amount of dust required to suppress X-rays this thoroughly, while simultaneously allowing the broad hydrogen lines and a fair amount of optical and infrared light to escape relatively unimpeded, demanded a very particular and somewhat contrived geometry. It was not impossible, but it required special pleading, a sign in physics that a theory may be patched together rather than fundamentally correct. A third line of explanation reached further back into theoretical astrophysics, toward a question cosmologists had been debating since long before Webb ever launched. How do supermassive black holes get so big so early? In the modern universe, black holes generally grow gradually, starting from a stellar remnant only a few times the mass of the Sun and slowly accumulating mass over billions of years. That gradual process struggles to explain how black holes containing millions or billions of solar masses could exist within the first several hundred million years after the Big Bang, simply because there has not been enough time for slow accretion to do the job. Two main alternative seeding mechanisms had been proposed well before little red dots were discovered, and both resurfaced as candidate explanations once the dots appeared. The first mechanism is called direct collapse. Under specific conditions, a large cloud of primordial gas that has not yet been enriched with heavier elements forged inside stars, can collapse directly into a black hole without ever passing through a normal stellar phase. Ordinarily, a collapsing gas cloud fragments into many smaller clumps, each one eventually igniting as an individual star. Because molecular hydrogen is an efficient coolant that lets gas lose energy and break apart into pieces. But if a nearby source of intense ultraviolet light, often an earlier forming galaxy, floods a gas cloud with what astronomers call Lyman-Werner radiation, that radiation can destroy the molecular hydrogen before it has a chance to cool the gas. Without that cooling, the entire cloud can collapse as one unbroken mass, skipping the fragmentation step entirely and forming a black hole seed weighing tens of thousands to, perhaps, 100,000 times the mass of the Sun in a single, dramatic event. rather than building up gradually from a much smaller, stellar remnant. The second mechanism relies on the universe's very first generation of stars, known as population 3 stars. These hypothetical stars, made purely of hydrogen and helium left over from the Big Bang, with none of the heavier elements that exist in every star astronomers have directly observed, are predicted to have been far more massive than typical stars forming today. In some models, reaching hundreds of times the mass of the Sun. Stars that massive burn through their fuel quickly and collapse into black holes after only a few million years, an eye blink on cosmic timescales. In dense, crowded environments, the resulting black hole remnants from many such stars could merge and grow rapidly through repeated collisions and rapid gas accretion, eventually building up to far larger masses within a few 100 million years. Both mechanisms, direct collapse and runaway population 3 remnant growth, could in principle explain the existence of unusually massive black holes very early in cosmic history. Neither one, on its own, fully explained the entire suite of properties seen in little red dots. The consistent reddening, the broad lines, the suppressed and the extreme compactness all appearing together across hundreds of separate objects in a way that looked less like a rare coincidence and more like a defined physical stage that a large fraction of early supermassive black holes pass through. That observation, that the properties of little red dots looked less like a one-off oddity and more like a shared evolutionary phase, turned out to be the key insight that eventually led toward an answer. In March of 2024, astronomer JWST and a team of colleagues published a study using data from 2 Webb surveys, named Eiger and Fresco, that formally catalogued and named this population for the first time, describing little red dots as an abundant class of faint active galactic nuclei at moderate to high redshift. That paper gave the field a shared vocabulary and a growing, well-defined sample to study, and it triggered an intense burst of follow-up work across multiple research groups through the rest of that year. Surveys like SEERS, JADES, and CosmosWeb each contributed their own discoveries, and the combined catalogue grew from dozens of objects to several hundred within about 18 months. As more little red dots were studied, individually rather than in large statistical samples, an additional clue emerged. Some of them appeared to be spinning rapidly. That detail strengthened the case that these were not simply unusual stellar populations, but compact systems organized around a central, massive, rotating structure consistent with a black hole and its surrounding disk of infalling material. At the same time, it deepened the puzzle, because rapid rotation around a massive central object is exactly the kind of system that should radiate strongly in X-rays, and these objects still were not. By the start of 2025, several independent theoretical groups had begun converging on a more specific physical picture, one that did not just say there is a black hole in there, but tried to explain precisely why that black hole would look the way little red dots actually look. The breakthrough came on the same day in March of 2025, when 3 separate research papers appeared online within hours of each other. One, eventually published in the journal Nature, was led by Anna de Graaf at the Center for Astrophysics, a joint institution of Harvard University and the Smithsonian. A second was led by Rohan Naidu at the Massachusetts Institute of Technology. The third came from the original Little Red Dot team around JWST. The 3 groups had been working largely independently, yet their conclusions lined up almost perfectly, which is exactly the kind of convergence that gives a scientific idea real weight. All 3 papers pointed toward the same underlying structure, a rapidly accreting supermassive black hole, surrounded not by a thin, relatively transparent accretion disk like the ones seen around nearby active galactic nuclei, but by a thick, dense cocoon of partially ionized gas. This cocoon behaves something like a one-way mirror built out of plasma. High-energy light, including the X-rays and much of the ultraviolet radiation generated near the black hole itself, gets absorbed almost completely by the dense surrounding gas before it can escape. That absorbed energy does not simply vanish, though. Conservation of energy demands it has to go somewhere. The gas cocoon re-radiates that absorbed energy at much lower, redder wavelengths in the optical and infrared, which is exactly the part of the spectrum where Webb sees these objects glowing so brightly. This single physical picture explained, in one stroke, 3 separate puzzles that had each resisted explanation on its own. The reddened 5-shaped spectrum stopped being a mystery. It is the natural signature of high energy, light being reprocessed and downshifted by a thick layer of surrounding gas. The missing X-rays stopped being a contradiction. The X-rays are not actually missing from the system. They are simply absorbed before they ever leave it. And the broad hydrogen emission lines found a more precise explanation, rather than tracing gas in smooth, ordered orbits around the black hole, the way a standard broadline region would. Much of the line broadening could come from electron scattering, photons bouncing repeatedly off free electrons inside the dense cocoon before finally escaping, smearing their wavelengths out in a distinctive way that differs, subtly but measurably, from ordinary orbital motion. Researchers began calling this configuration a black hole star, a term meant to capture something genuinely strange about its appearance from the outside, looked at from a distance, with only modest spectral resolution. A black hole wrapped in a dense, glowing gas envelope can resemble an enormous, cold, almost stellar object, radiating steadily from what looks like a single, compact surface, even though there is no actual stellar interior, no nuclear fusion, and no solid or liquid surface anywhere inside it. The star in the name is descriptive rather than literal. It describes how the object behaves observationally, not what it actually is made of underneath the gas. If you have made it this far into the explanation, this is roughly the point in the story where most people watching start wanting to know what happens next. And that curiosity is exactly the right instinct to follow, because it is also the question that drove the next major leap forward in this research, which came only a few months ago and finally pushed the evidence from compelling to something close to definitive. If that kind of careful, evidence-driven unraveling of a genuine cosmic mystery is interesting to you, following along and subscribing means you will not miss the next discovery like this one. And there is a fair chance the next one is even stranger. The black hole star model was elegant. It tied together loose threads that had been dangling separately since 2022. But an elegant model is not automatically a confirmed one, and for most of 2025, that is exactly the status this idea held. The leading hypothesis, strongly supported, but still short of the kind of overwhelming, multi-line spectroscopic proof that settles a scientific debate for good. Getting that proof required something little red dots almost never offer enough light. Before getting to that breakthrough, it is worth addressing a phrase that had been circulating in popular science coverage since shortly after little red dots were first discovered. The claim that Webb had broken cosmology. That phrase came from a real and serious concern, not just a dramatic headline. If the original mass estimates for these black holes were correct, taken at face value from the broadline widths under the assumption of ordinary orbital motion, then the universe appeared to contain far more extremely massive black holes, far earlier than standard models of structure formation predicted should be possible, even accounting for fast-growing seed mechanisms like direct collapse or runaway population 3 mergers. Either the seeding and growth models were fundamentally wrong, or something was inflating the mass estimates themselves. the electron scattering insight buried inside. The black hole star model offered a direct resolution to that puzzle, and a study led by researcher Rusakov, published in Nature in January of 2026, worked out exactly how large the effect was. Using a sample of 12 little red dots with sufficiently detailed spectra, the team showed that a meaningful portion of the broad line width in these objects comes not from gas orbiting at genuinely enormous velocities, close to the black hole, but from photons scattering repeatedly off free electrons in the surrounding dense cocoon. That scattering broadens emission lines in a way that mimics, but is physically distinct from, the broadening produced by fast orbital motion. Standard black hole mass formulas, built and calibrated using nearby, unobscured active galactic nuclei, were never designed to account for this extra scattering component, so when applied directly to little red dots, they systematically overestimated the implied black hole mass. Once the team corrected for the electron scattering contribution, the implied black hole masses dropped dramatically, by roughly a factor of 100 in many cases. Objects that earlier analyzers had placed in the range of hundreds of millions or even billions of solar masses turned out, after correction, two more plausibly fall somewhere between roughly 100,000 and 10 million solar masses. That corrected range fits comfortably within what standard models of early black hole growth, including both the direct collapse and population 3 seeding channels, can plausibly produce within the first 1 billion years of cosmic history. The universe, in other words, had not broken any rules. Astronomers had simply been looking at it through gas they did not yet know was there, gas that was distorting their measuring stick. This was an important correction, but it still left an open question. The black hole star model explained the broad strokes of little red dots collectively, and the Rusakov paper explained why mass estimates had run too high, but no single object had yet produced a spectrum detailed enough to test every individual prediction of the model at once, line by line, feature by feature, with enough precision to rule out every remaining alternative for that specific source. Most little red dots, even with Webb's considerable sensitivity, are simply too faint at their extreme distances to yield that level of spectral detail. A typical little red dot spectrum reveals only the brightest handful of emission features, enough to support the general picture, but not enough to nail it down with certainty for any one object. What the field needed was a stroke of luck, one little red dot, positioned in just the right place in the sky, that nature itself would help observe more deeply than Webb could manage on its own. In June of 2026, that stroke of luck arrived, and it came from one of the oldest tricks in observational astronomy, a trick first predicted by Albert Einstein over a century earlier. Gravitational lensing relies on a simple but profound consequence of general relativity, the theory of gravity published by Albert Einstein in 1915. Mass does not just attract other mass through an invisible force, the way Isaac Newton's earlier theory described it. Mass actually warps the geometry of space and time around it, and light traveling through that warped space follows a curved path. Even though the light itself has no mass and is simply moving in the straightest line available within a bent landscape, Einstein predicted that this effect would be measurable. Light from a distant star passing close to the sun should appear to shift position slightly, bent by the sun's gravitational field. In May of 1919, during a total solar eclipse that briefly blocked the sun's overwhelming glare, two expeditions led by the astronomer Arthur Eddington measured exactly that shift, confirming Einstein's prediction and transforming general relativity from an elegant mathematical theory into an experimentally verified description of reality. Massive galaxy clusters, containing the combined gravity of thousands of galaxies along with enormous quantities of invisible dark matter, bend light far more dramatically than a single star ever could. When a cluster sits directly between Earth and a much more distant background object, the cluster's gravity can act as a natural lens, bending and concentrating the background object's light, sometimes magnifying it, stretching it into arcs, or even splitting a single source into multiple separate images. For astronomers studying extremely faint, extremely distant objects, a foreground cluster acting as a gravitational lens is close to the closest thing nature offers to a free upgrade on telescope size. Webb does not need to be any bigger or any more sensitive. The cluster itself does part of the magnification work for free, using nothing but its own gravity. A research program named GLIMPSE was designed specifically to take advantage of this effect. Led by Hakim Atek of the Institut d'Astrophysique de Paris, the GLIMPSE program pointed Webb at a handful of massive foreground galaxy clusters with the explicit goal of finding the faintest possible background sources, including, ideally, examples of the universe's hypothetical first generation of stars, the population 3 stars discussed earlier, along with extremely faint early galaxies that would otherwise sit below Webb's detection threshold without the extra boost from lensing. One of the clusters targeted by the GLIMPSE program was Abell S1063, a massive cluster whose gravity has been mapped in detail by previous Hubble and Webb observations, specifically because of its lensing power. Behind that cluster, at a redshift of 3.5, sat an object that the survey catalogued under the designation GLIMPSE-17775. A redshift of 3.5 corresponds to light that left its source when the universe was approximately 1.8 billion years old, placing this particular little red dot near the tail end of the population's roughly 1 billion year window of existence, closer to the era when little red dots, as a class, begin disappearing from later, more mature surveys. GLIMPSE-17775 was not the primary target of the observation. It happened to sit in the right place at the right time, magnified by Abell S1063's gravity well enough to stand out as an unusually promising little red dot for deeper study. Webb devoted roughly 30 hours of direct observing time to gathering its spectrum. Thanks to the cluster's gravitational magnification, that 30 hours of telescope time produced a signal equivalent in quality to what would normally require something closer to 80 hours of unmagnified observation. In practical terms, the lensing effect nearly tripled the depth of the resulting spectrum without costing any additional telescope time at all. That extra depth turned out to be exactly what the field needed. Most little red dot spectra, even good ones, show perhaps a handful of identifiable emission features, the broad hydrogen lines, maybe 1 or 2 other prominent lines, and not much else above the noise. The GLIMPSE-17775 spectrum, published by a team led by Vasily Kokorev at the University of Texas at Austin, contained more than 40 separate, individually identifiable spectral lines. By far the most detailed spectrum ever obtained for any object in this class. With that many independent measurements available simultaneously, researchers finally had enough information to test the black hole star model rigorously, feature by feature, rather than relying on a handful of headline characteristics that could plausibly fit more than one competing explanation. The Kokorev team's analysis of those 40-plus lines reads almost like a checklist of independent confirmations, each one probing a different physical aspect of the system, and each one landing on the same conclusion. The first major piece of evidence concerned the shape of the broad hydrogen lines themselves. As discussed earlier, ordinary broadline regions around active galactic nuclei produce line broadening through orbital motion, gas clouds, circling the black hole at different distances and velocities, following what is known as Keplerian motion, the same physics that governs how planets orbit the Sun, just on a vastly more energetic scale. Keplerian broadening produces a particular, recognizable line profile, electron scattering. The mechanism proposed by the black hole star model produces a noticeably different profile because it depends on photons bouncing repeatedly off free electrons in a dense medium, rather than tracing the orbital velocity of distant gas clouds directly. The GLIMPS 17775 spectrum showed line profiles consistent specifically with electron scattering, not simple Keplerian orbital broadening. That distinction mattered enormously, because it meant the line width was not just confirming there is fast-moving gas here, a fact several theories could explain, but was instead pointing at a very specific structure, a dense, optically thick gas envelope surrounding the black hole. Exactly as the black hole star model predicted, the second major piece of evidence came from what astronomers call an iron forest, a dense thicket of overlapping emission lines produced by singly ionized iron atoms. This particular spectral signature is well documented in the broadline regions of nearby, well-studied active galactic nuclei, and it requires very specific physical conditions: high gas density, particular ionization states, and a strong radiation field capable of exciting iron atoms into the right energy states to produce that exact pattern of lines. Finding a clear iron forest in GLIMPS 17775 spectrum provided independent confirmation that the conditions inside this object matched known active galactic nucleus broadline region physics far more closely than they matched a starburst galaxy or any purely stellar explanation. The third piece of evidence involved absorption features from helium, rather than emission features. Absorption lines form when gas in front of a light source removes specific wavelengths from the light passing through it. The same basic principle behind the dark lines astronomers use to determine what elements exist in the Sun's outer atmosphere. The particular helium absorption pattern detected in GLIMPS 17775 indicated a region of highly ionized gas that had been stripped of electrons by an intense radiation field, sitting somewhere along the line of sight between the central engine and the observer. That kind of highly ionized absorbing gas is consistent with exactly the dense, irradiated cocoon the black hole star model describes, a layer close enough to the black hole to be bathed in extreme radiation, but positioned so its absorption signature shows up clearly in the spectrum-reaching web. The fourth piece of evidence came from a set of fluorescence features, spectral lines produced when atoms absorb high-energy, ultraviolet photons, and then re-emit that energy at a different, characteristic wavelength, a process closely related to how certain materials glow under black light. These particular fluorescence transitions only appear under an intense ultraviolet radiation field, the kind generated efficiently by accreting black holes in a disk, and not by ordinary star formation, which produces ultraviolet light far less efficiently and across a broader, less concentrated range of energies. Their presence ruled out star formation as the dominant power source and pointed specifically toward an accretion-powered central engine. Individually, any one of these four lines of evidence might have been explained away by some alternative model with enough special pleading. Together, appearing simultaneously in a single, exceptionally deep spectrum with no contradictory feature requiring a separate explanation, they amounted to the strongest case yet assembled for the black hole star model applied to any individual little red dot. As Kokorev's team described it, previous studies of little red dots had each captured a piece or two of relevant evidence, but no earlier observation had managed to gather every diagnostic piece from a single object at once. Glimpse 17775 finally did. This new result also closed the loop on the broken cosmology concern raised earlier. The original alarm came from black hole mass estimates that, taken at face value, implied early supermassive black holes growing far faster and far bigger than standard structure formation models allowed. Even with the fastest plausible seeding mechanisms, the electron scattering correction described in the Rusakov paper, now reinforced by a direct line-by-line confirmation from Glimpse 17775 that electron scattering really is the dominant broadening mechanism in at least one well-studied case, removes most of that tension. Once corrected for the dense gas cocoon's effect on the spectrum, the implied black hole masses settle into a range that standard, early universe black hole growth models can comfortably explain. The universe's early black holes are still remarkable, enormous relative to their tiny host systems, growing astonishingly fast by any reasonable standard, and producing energy outputs that dwarf entire modern galaxies from regions barely larger than a solar system. But they are no longer outright impossible. The phrase broken cosmology described a real measurement problem, not a flaw in the universe's actual behavior. That resolution does not mean every question about little red dots has been answered. Kokorev and his collaborators were careful to note that their result confirms the black hole star model decisively for one specific, exceptionally well-observed object, not automatically for the entire catalogue of more than 341 known little red dots. Most of those other objects are far too faint, even with Webb's sensitivity, to produce a spectrum anywhere near this detailed without their own lucky gravitational lens. Researchers now treat Glimpse 17775 as a kind of reference template, a benchmark spectrum against which future, less detailed observations of other little red dots can be compared, to check whether the broader population is genuinely uniform, or whether some fraction of these objects might still turn out to be something different. One alternative explanation that has not been fully ruled out involves an entirely different and even stranger kind of object: supermassive primordial stars. A separate team at the Harvard Smithsonian Center for Astrophysics proposed in January of 2026 that at least some little red dots might represent an extreme, short-lived stage in the life of a population 3 star, one that managed to grow to an enormous mass, potentially in the range of 1 million solar masses or more, before finally collapsing under its own gravity into a black hole. In this scenario, what Webb captures is not a black hole already formed and actively feeding, wrapped in a reprocessing gas cocoon, but rather the star itself in the final stages of its life, just before that collapse occurs, distinguishing cleanly between an enormous star about to become a black hole and a newly formed black hole wrapped in a dense, partially ionized gas envelope is observationally difficult, because both scenarios can, in principle, produce broadly similar spectral signatures under certain conditions. Researchers in the field generally expect this question, whether some little red dots are pre-collapsed supermassive stars rather than already formed black hole stars, to be resolved within the next year or two. As more deeply lensed examples like Glimpse 17775 become available for detailed study, there is also the matter of formation. Even if the black hole star model is correct for the large majority of little red dots, that model describes what these objects are during this particular phase of their existence. It does not, by itself, settle the older question of how the underlying black holes got so big so quickly in the first place. Did most little red dot black holes begin as direct collapse objects, skipping the stellar phase entirely and forming from a single, massive, pristine gas cloud bypassing fragmentation? Did they begin instead as much smaller population 3 stellar remnants that grew explosively fast through repeated mergers and extreme accretion in dense early star clusters? Or did different little red dots form through different channels, with the observed population representing a mixture of formation histories that all happened to pass through a similar gas-cocooned observational stage on their way to becoming more ordinary, visible quasars later on? The current data cannot yet distinguish cleanly between these possibilities, and resolving that question will likely require a combination of more detailed spectroscopy, more sophisticated theoretical simulations of early gas cloud collapse, and eventually direct evidence, if it can ever be found, of population 3 stars themselves, which remain entirely unobserved directly as of today, existing in current astrophysics only as a strongly motivated theoretical prediction. Finally, there is the question of why little red dots disappear from later surveys after roughly 1.6 billion years post-Big Bang. 2 explanations are currently favored, and they are not mutually exclusive. One possibility is that the dense gas cocoon surrounding each black hole eventually gets consumed, blown away by the black hole's own radiation pressure, or otherwise dispersed as the system evolves, revealing a more conventional, unobscured active galactic nucleus underneath, the kind already well known and well studied throughout the rest of cosmic history. Under this view, little red dots are not a separate species of object that goes extinct, but rather a brief, characteristic life stage that essentially every early supermassive black hole passes through before settling into a more familiar, visible adulthood. The other possibility relates to the specific conditions of the early universe itself, the gas-rich, chaotic, rapidly assembling environment that made it easy to feed a black hole at extreme cocoon-sustaining rates may simply become rarer as the universe ages. Galaxies settle into more orderly structures, and the easily available reservoirs of cold, dense gas get consumed or dispersed. In that view, the population is partly a feature of the era's overall gas dynamics, not solely an internal evolutionary clock running inside each individual black hole dot. To appreciate just how unusual little red dots are, it helps to step back and look at the broader history of how astronomers came to understand actively feeding black holes in the first place, because that history shows just how far this particular puzzle sits outside the normal range of behavior. The first hints that some galaxies harbor unusually energetic centers came in 1943, when astronomer Carl Seyfert identified a small class of galaxies with unusually bright, compact nuclei and broad emission lines, a class that would later bear his name, Seyfert galaxies. For nearly 2 decades afterward, these objects remained a curiosity, interesting but not obviously connected to anything more dramatic. That changed in 1963, when astronomer Martin Schmidt analyzed the spectrum of an object known as 3C273, a source originally catalogued simply as an unusually strong radio emitter. Schmidt realized that its spectral lines, initially puzzling, made sense if the object's light was redshifted by an enormous amount, placing it at a staggering distance, far beyond any normal galaxy, yet still appearing as a single, star-like point of light through ordinary telescopes. These objects became known as quasi-stellar radio sources, shortened over time to quasars. Quasars turned out to be among the most luminous objects in the universe, often outshining their entire host galaxy by factors of dozens or more. And the eventual explanation settled on a supermassive black hole at the galaxy's center, consuming surrounding gas and converting a fraction of that in falling matter's mass directly into radiated energy with remarkable efficiency, far higher than the efficiency of nuclear fusion inside ordinary stars. By the 1980s and 90s, astronomers had developed what is now called the unified model of active galactic nuclei, the idea that quasars Seyfert galaxies, and several other previously distinct-seeming categories of energetic galaxy nuclei are fundamentally the same underlying phenomenon: a feeding supermassive black hole surrounded by an accretion disk and a dusty, donut-shaped structure called a torus, viewed from different angles. Look at the system face-on, and the bright accretion disk and broad-line region are directly visible, producing a classic quasar or Seyfert 1 spectrum. Look at the same system edge-on, with the dusty torus blocking the direct view of the central engine, and the same underlying object appears as a different, more obscured category entirely. This insight that orientation alone could explain much of the diversity seen among active galactic nuclei was a major unifying success in extragalactic astronomy, and it gave researchers a well-tested framework for interpreting almost every actively feeding black hole observed for the following 30 years. Little red dots do not fit neatly into that unified framework either, which is part of why they proved so disruptive when Webb first found them. A simple, dusty, edge-on torus can explain reddening and modest X-ray obscuration, but it struggles to explain the near-total absence of X-rays seen across the little red dot population as thoroughly and consistently as the black hole star model does, and it does not naturally predict the specific V-shaped continuum, the electron scattering line profiles, or the particular combination of iron forest, helium absorption, and fluorescence features confirmed in GLIMPS 17775. The black hole star model effectively describes a new category that the unified model never anticipated, not a black hole viewed edge-on through an external, dusty torus, but a black hole still embedded inside its own dense, self-generated gas envelope, a structure tied to an early, transient phase of extremely rapid growth, rather than two viewing angle at all. There is a useful physical concept underlying why this rapid growth phase produces such an unusual structure, something astronomers call the Eddington limit, named after the same Arthur Eddington who confirmed Einstein's light-bending prediction in 1919. The Eddington limit describes a theoretical maximum rate at which an object can accrete matter, while still letting that matter fall inward smoothly. As gas spirals toward a black hole and heats up, it radiates outward, and that outward flowing radiation exerts pressure on the infalling material, pushing back against gravity. Below the Eddington limit, gravity wins, and gas falls in steadily. Push the accretion rate higher, toward or beyond the Eddington limit, and radiation pressure starts pushing back hard enough to puff the inner accretion structure outward, thicken it, and drive some material away in outflows. Even as the black hole continues consuming gas at the center, many of the little red dots studied so far appear to be accreting at rates close to, or in some cases significantly beyond, this Eddington limit, a regime astronomers call super-Eddington accretion. Super-Eddington growth lets a black hole gain mass extremely quickly, which helps explain how these objects could reach such large masses within the universe's first 1 billion years. But it naturally produces exactly the kind of thick, radiation, geometrically puffed up structure that the black hole star model describes. Not a thin, well-ordered accretion disk, but a dense, turbulent, partially ionized envelope, exactly thick enough to trap and reprocess the black hole's high-energy light before it escapes. Super-Eddington accretion, in other words, may be both why these black holes could grow so fast in the early universe, and why they look the way they do once Webb observes them. For comparison, the supermassive black hole at the center of our own Milky Way galaxy, named Sagittarius A star, contains roughly 4 million times the mass of the Sun and is currently accreting extremely slowly and quietly, producing only a faint trickle of radiation compared to its theoretical maximum. The black hole at the center of the galaxy M87, the first black hole ever directly imaged by the Event Horizon Telescope collaboration in 2019, contains roughly 6.5 billion solar masses and likewise accretes at a relatively modest rate today. Little red dot black holes, by contrast, despite often having far smaller masses than M87's central black hole, are believed to be feeding at rates close to or beyond their own Eddington limits, a dramatically more frantic and energetic phase of growth than almost anything observed in the relatively calm, well-studied black holes of the present-day universe, with one object now confirmed in exceptional detail. The obvious next step is finding more like it, and astronomers already have a clear strategy for doing exactly that. Massive galaxy clusters capable of strong gravitational lensing are not rare. Dozens of them have already been mapped in detail by Hubble and Webb, including well-studied clusters such as Able to 744, Max J0416, and the cluster used in this discovery, Able S1063. Each of these clusters magnifies a different patch of background sky, and statistically, given how common little red dots turned out to be once Webb started looking carefully, it would be surprising if at least a handful of other lensed little red dots were not sitting behind these well-mapped clusters already, waiting for a sufficiently deep, targeted spectroscopic follow-up observation. Researchers are now planning dedicated observing campaigns specifically designed to search known lensing clusters for additional examples, prioritizing any little red dot candidate that happens to sit in a region of unusually strong magnification. If even a handful of additional objects produce spectra of similar depth and quality to Glimpse 17775, and all of them show the same convergent suite of evidence, that would transform the black hole star model from confirmed for one object into confirmed as the standard explanation for the entire class, closing off the remaining uncertainty about whether the broader population is genuinely uniform. If, on the other hand, some of those follow-up targets turn out to show a different spectral signature entirely, lacking the iron forest, or showing Keplerian rather than electron scattering line profiles, that would indicate the little red dot population is not a single uniform phenomenon, but rather a mixed bag of different objects that happen to share a similar broad color and luminosity range without sharing the same underlying physical structure. Beyond opportunistic lensing, several major upcoming observatories are expected to contribute directly to this research over the next decade. The Nancy Grace Roman Space Telescope, expected to begin science operations later this decade, is designed to survey enormous areas of sky, far larger than Webb's relatively narrow field of view, at infrared wavelengths well suited to detecting little red dots in much greater numbers than the current catalogue of 341 objects. A wide survey like Roman's could plausibly multiply the known sample by a factor of 10 or more, providing the large statistical numbers needed to study how little red dot properties vary with cosmic time, environment, and host galaxy characteristics. Rather than relying on a relatively small number of individually studied examples, on the ground, the extremely large telescope, currently under construction in Chile and expected to begin operating before the end of this decade, will feature a primary mirror roughly 39 meters across, several times larger than any existing optical or infrared telescope, giving it the light-gathering power to obtain detailed spectra of fainter, more typical little red dots without needing the lucky assistance of a gravitational lens at all. Combined with adaptive optics systems that correct for the blurring effects of Earth's atmosphere in real time, the extremely large telescope should eventually be able to study dozens of little red dots with something approaching the spectral depth currently available only for the single Fortunately, lensed glimpse 17775 X-ray astronomy is also expected to play a continuing role, despite, or perhaps because, of the puzzling X-ray weakness already documented in this population. Current X-ray observatories, including Chandra and the European Space Agency's XMM, lack the sensitivity to detect most individual little red dots, even with very long exposure times, which is part of why researchers have had to rely on statistical stacking techniques rather than individual detections. Proposed next-generation X-ray missions, including concepts known as LINX and AXIS that have been studied by NASA in recent years, would offer substantially improved sensitivity at the relevant wavelengths. If even one of these proposed missions eventually flies, it could finally test directly whether little red dots are truly producing almost no X-rays at the source, consistent with extreme absorption by a thick gas cocoon, or whether some X-ray emission does exist but currently sits just below the detection threshold of every X-ray telescope built so far. Webb itself, meanwhile, continues to be the primary workhorse for this entire field, and researchers are already planning deeper, more targeted spectroscopic campaigns specifically aimed at little red dots, building directly on the techniques that produced the glimpse 17775 result. Longer integration times, carefully chosen targets behind known lensing clusters, and improved data reduction techniques that better separate a faint, little red dots, light from the bright foreground. Cluster galaxies surrounding it are all expected to push the depth and quality of future little red dot spectra closer to, and potentially beyond, what was achieved for this one exceptional object. Little red dots are not the only surprise Webb turned up once it started examining the universe's first billion years in detail, and understanding some of the other surprises helps explain why this particular discovery generated so much attention rather than being treated as a narrow, specialized puzzle confined to a small corner of astrophysics. Almost immediately after, Webb's first deep field images arrived in the summer of 2022. Several research teams identified candidate galaxies that appeared to be both extremely distant and, troublingly, extremely massive for their age. Standard models of galaxy formation predict that it takes a certain amount of time for gas to collapse, stars to form, and a galaxy to build up a substantial stellar mass. Time that scales, broadly speaking, with the age of the universe at that point. Some of Webb's earliest candidate galaxies appeared to contain stellar masses that seemed difficult to reconcile with the relatively short amount of time available since the Big Bang. Given standard assumptions about how efficiently gas converts into stars, a handful of widely discussed papers in late 2022 and early 2023 suggested these impossibly early, massive galaxies might represent a serious challenge to the standard cosmological model, sparking similar broken cosmology-style headlines well before little red dots themselves became the most prominent example of that broader narrative. Subsequent, more careful analysis worked through several of these cases individually. In some instances, improved spectroscopic redshift measurements showed the galaxies were not quite as distant, and therefore not quite as improbably massive for their age, as initial photometric estimates had suggested. In others, refined stellar mass estimates, accounting more carefully for the presence of an active galactic nucleus contributing extra light on top of the galaxy's actual star content, brought the inferred stellar mass down into a range standard models could comfortably accommodate. The broader population of unusually massive early galaxies has not vanished entirely from the conversation, and some tension between observations and the simplest versions of standard galaxy formation models persists in the research literature even today. But the most extreme, Headline-grabbing claims of outright cosmological crisis have largely been resolved through more careful measurement, in a pattern that closely echoes what eventually happened with little red dots themselves, an apparent contradiction with standard physics, followed by the realization that the contradiction stemmed partly from how the measurements were being made, rather than from the universe genuinely breaking its own established rules. This recurring pattern, dramatic seeming anomaly, followed by careful remeasurement, followed by a less dramatic but still genuinely interesting resolution, is worth noting because it reflects something true about how observational astronomy generally proceeds at the frontier of what current instruments can detect. Webb is observing fainter, more distant, more extreme objects than any previous telescope, often pushing right up against the edge of what its instruments can reliably measure. At that edge, ambiguous or partially understood physical effects, like the electron scattering inside a little red dot's gas cocoon, or the contaminating light from an active nucleus inside an apparently overly massive early galaxy, can distort initial measurements in ways that only become clear after additional data, deeper spectra, or improved theoretical modeling catches up. None of this makes the original anomalies any less worth investigating. Quite the opposite. It simply means that the most exciting initial headline is rarely the final scientific answer, and the genuinely interesting science often lives in the careful, sometimes years-long process of figuring out exactly why an apparent anomaly looked the way it did. This broader context also connects to a deeper, related mystery that remains entirely unresolved: the direct detection of population 3 stars. Despite extensive searching, including dedicated survey programs like GLIMP specifically designed to hunt for them using gravitational lensing assistance, no confirmed, unambiguous example of a genuine population 3 star has yet been found. Every existing model of the early universe predicts they should have existed, forming out of pristine, metal-free gas within the first few 100 million years after the Big Bang, burning extremely hot and extremely bright, and dying quickly in spectacular fashion. Yet, despite Webb's substantial improvements in sensitivity and its specific targeting of likely population 3 environments, the search continues without a confirmed detection. Some researchers consider it plausible that a handful of unusual objects already catalogued, including possibly some little red dots, interpreted not as black hole stars but as the alternative, supermassive, primordial star scenario discussed earlier, could turn out to represent indirect evidence connected to this stellar population, even if a clean, unambiguous, individual population 3 star detection continues to remain just out of reach. There is also a cosmological angle to little red dots worth examining. The era in which they exist overlaps almost exactly with what astronomers call the epoch of reality, one of the most important transitions in the universe's entire history. For roughly the first few 100,000 years after the Big Bang, the universe was dense and hot enough that matter existed as a plasma, electrons and protons too energetic to combine into stable, neutral hydrogen atoms. As the universe expanded and cooled, neutral hydrogen finally formed everywhere, and the universe became transparent to light for the first time, an event astronomers call recombination, whose afterglow survives today as the cosmic microwave background radiation. For hundreds of millions of years after that, the universe existed in a state often called the cosmic dark ages, filled with neutral hydrogen gas, with no significant sources of light, yet bright enough to illuminate it broadly. That changed once the first stars and the first active galactic nuclei began producing enough high-energy, ultraviolet radiation to start stripping electrons back off the neutral hydrogen atoms, filling intergalactic space, a process called which transformed the universe's diffuse gas back into an ionized state, this time permanently, since the universe has continued expanding and cooling ever since without reforming that early neutral hydrogen on a large scale. Reionization is generally thought to have been largely complete by around 1 billion years after the Big Bang, which places it squarely within the same cosmic window where little red dots are most abundant dots. This timing connection raises an interesting question that researchers are actively investigating. Did little red dots, or the black holes inside them, contribute meaningfully to reionizing the universe? Active galactic nuclei are, in principle, efficient producers of ionizing ultraviolet radiation, the exact kind of light needed to strip electrons from hydrogen atoms across vast stretches of intergalactic space. If little red dots are indeed black holes generating large amounts of ionizing radiation internally, as the black hole star model suggests, their contribution to cosmic reionization depends heavily on how much of that ionizing light actually escapes the dense surrounding gas cocoon rather than being absorbed and reprocessed into the redder light Webb directly observes. Current evidence suggests the cocoon absorbs the great majority of that high-energy light internally, which would mean little red dots, despite producing enormous amounts of ionizing radiation at their source, contribute comparatively little directly to reionizing the broader intergalactic medium, leaving that job mostly to ordinary star-forming galaxies and to active galactic nuclei that have already shed their gas cocoons and become more directly visible. This remains an active area of study, and the exact balance between these different ionizing sources during this critical era is still being worked out. There is also a connection worth drawing between little red dots and the well-established relationship between black holes and their host galaxies in the present-day universe, the M-sigma relation discussed earlier. That relationship did not appear out of nowhere. It almost certainly reflects some kind of physical feedback process, linking a galaxy's central black hole to the broader galaxy surrounding it, even though the precise mechanism connecting the two remains debated. One leading idea involves the black hole's own radiation and outflows eventually growing powerful enough to heat or expel large amounts of the surrounding galaxy's gas that would otherwise have continued forming new stars, effectively limiting how large both the black hole and its host galaxy can grow together over cosmic time, a process generally called active galactic nucleus feedback. If little red dots represent the earliest, most extreme phase of black hole growth, a phase where the black hole has already grown disproportionately large relative to its still tiny, still forming host galaxy, they may represent a kind of cosmic starting condition for this feedback relationship, an early imbalance that subsequent feedback processes gradually correct over the following billions of years, eventually producing the much tighter, more balanced relationship astronomers observe between black holes and galaxies throughout the much later, much more mature universe we inhabit today. Confirming or refining that picture will likely require tracking how the black hole-to-galaxy mass ratio evolves across cosmic time, using larger samples of little red dots at a range of different redshifts within their roughly 1 billion year window of existence. Work that is only just beginning, given how recently this object class was even properly identified. It is worth dwelling for a moment on the physical scale and structure implied by the black hole star model, because the numbers involved are difficult to grasp intuitively, even by the standards of astrophysics. A field already full of difficult-to-grasp numbers. A black hole's event horizon, the boundary beyond which nothing, not even light, can escape its gravity, has a size that scales directly with mass, a relationship described by what is called the Schwarzschild radius. For a black hole containing roughly 1 million solar masses. Near the lower end of the corrected mass range found 4 little red dots. The event horizon would measure only a few million kilometers across, smaller than the orbit of Mercury around the Sun, yet the gas cocoon surrounding that event horizon in the black hole star model extends vastly farther outward, likely spanning a region comparable in scale to an entire solar system, dense enough and extended enough to absorb and reprocess essentially all of the high energy radiation generated near the event horizon before any of it can escape directly. The contrast in scale, an event horizon smaller than a single planetary orbit, wrapped inside a reprocessing gas envelope as large as an entire solar system, helps explain why a system this physically extreme can still appear from many trillions of kilometers away, simply as one of the universe's many faint, compact, reddish points of light. The temperature structure inside that cocoon also helps explain the observed spectrum. Deep inside, close to the black hole's accretion disk, temperatures reach millions of degrees, hot enough to generate the X-rays and hard ultraviolet light that the cocoon then absorbs. Moving outward through the gas envelope, the absorbed energy gets reprocessed and re-emitted repeatedly, gradually shifting toward lower energies and longer wavelengths each time it interacts with the surrounding gas, until the radiation that finally escapes into space, the radiation Webb actually detects, carries a far cooler effective temperature, typically estimated somewhere in the range of several thousand degrees, comparable in some respects to the surface temperature of an ordinary, if unusually luminous, star. That apparent surface temperature, combined with the object's compact size and steady, star-like point source appearance, is precisely what inspired the black hole star terminology in the first place. An object that looks superficially and from a distance remarkably like an enormous, luminous, relatively cool star, while actually being powered by an entirely different mechanism hidden inside, capturing a spectrum detailed enough to detect features like the iron forest and the specific helium absorption pattern required. Webb's near-infrared spectrograph instrument, commonly abbreviated AIS-PACX, operating in a mode that uses a microshutter array, a grid of thousands of individually controllable tiny shutters that can be opened or closed to select exactly which faint background sources to observe while blocking out unwanted light from brighter, closer objects in the same field of view, including the numerous foreground galaxies that make up the lensing cluster itself, separating glimpse 17775's faint, lensed light from the much brighter light of Abell S1063's own member galaxies required. Careful modeling of the cluster's overall light distribution, subtracting that modeled foreground light from the data before the underlying spectrum of the background, little red dot could be cleanly extracted and analyzed. This kind of careful foreground subtraction is now a standard, if still painstaking, part of essentially every gravitationally lensed deep field observation Webb performs. The broader surveys that built up the little red dot catalog over the preceding several years used complementary but distinct observing strategies. The CERS survey, led by Stephen Finkelstein at the University of Texas at Austin, used Webb's imaging and spectroscopic capabilities across a region of sky previously studied by Hubble's CANDLE survey, allowing direct comparison between what Hubble could and could not detect in the same patch of sky. The JWST survey, a collaboration centered partly around the near-infrared camera and UNR-aspect instrument teams, pushed particularly deep into the area surrounding the original Hubble ultra-deep field, building on decades of accumulated knowledge about that specific, well-studied patch of sky. COSMOS Webb, one of the largest single Webb observing programs by total area, surveyed a much wider patch of sky at somewhat shallower depth, trading some sensitivity to the very faintest objects for a much larger total sample size, which proved valuable for building robust statistics on how common little red dots are across different regions of sky, rather than relying on a single small, deep field that might not be representative of the broader universe. There is something worth noting about how this particular scientific result came together, beyond the physics itself, because it illustrates how modern astrophysics research actually proceeds at its best. The three foundational papers from March of 2025, led independently by de Groff, Nadu, and Mathy, were not the product of a single coordinated announcement. Each team had been working with its own data, its own analysis methods, and largely independently of the other two. Yet all three converged on essentially the same physical picture and posted their preprint papers publicly within hours of one another. In modern astrophysics, researchers routinely post preprints, early versions of papers not yet finalized through formal peer review, to a shared public archive before formal publication, allowing the broader community to see and respond to new results quickly rather than waiting months or years for the traditional review and publication process to run its course. When three independent teams converge on the same conclusion through three independent paths, all visible to the community within the same narrow window, that kind of convergence carries significantly more weight than any single paper could on its own, precisely because it was not coordinated, and any one team's particular methodological choices or assumptions are far less likely to be driving the shared result by coincidence. The same pattern of independent convergence shows up again in the Rusakov mass correction paper from January of 2026, published separately from, though clearly building on, the original black hole star proposals from the previous year, and again in the Kokorev team's Glimpse 17775 analysis just months later, which itself drew on theoretical predictions from the earlier papers to know specifically which spectral features to search. For once, the unusually deep spectrum became available. Science of this kind rarely advances through a single decisive experiment that settles everything at once. It tends to advance the way this story has unfolded: an unexpected observation, several years of competing partial explanations, a gradual convergence among independent research groups toward a shared physical model, a careful correction to an earlier measurement once the model's full implications become clear, and finally, when the right combination of a rare astronomical alignment and a sufficiently sensitive instrument comes together, a single result detailed enough to move the leading hypothesis from well-supported to something close to settled. At least for one particularly well-observed example, none of this means the story is finished. Even with Glimpse 17775's confirmation, researchers studying little red dots are already focused on the next set of open questions: whether the broader population is uniform or mixed, exactly which seeding mechanism, direct collapse, runaway population 3 mergers, or some combination, actually produced the underlying black holes, how the black hole star phase eventually ends and what that transition looks like in detail, and how all of this fits into the still developing picture of how galaxies and their central black holes grow together across the full span of cosmic history. Each of those questions points toward observations and instruments that either already exist and simply need more time pointed at the right targets, or are currently under construction and will not be ready for several more years. The pace of discovery in this particular corner of astrophysics has been remarkably fast since 2022, and there is little reason to expect that pace to slow down soon, given how many major new facilities are scheduled to come online over the next decade. Step back far enough from the details of gas, cocoons and electron scattering in broadline regions, and little red dots connect to one of the oldest and largest questions in all of cosmology. Why does the universe look the way it does? And where do its starting conditions ultimately come from? The black holes inside little red dots grew as fast as they did because the very early universe provided exactly the right raw materials. Large reservoirs of cold, dense, mostly pristine gas, assembled into the right configurations at the right cosmic moment to allow either direct collapse or extremely rapid stellar remnant growth to occur. Those gas reservoirs themselves trace back to slightly denser regions within the broader, nearly uniform distribution of matter that filled the universe shortly after the Big Bang. Regions that grew denser over time purely through the action of gravity, pulling slightly more matter towards slightly overdense patches, in a process cosmologists call gravitational structure formation. Those original overdense patches, in turn, trace back to extremely small, essentially random quantum fluctuations, tiny variations in the density of the universe's contents that existed when the entire observable universe was compressed into a volume far smaller than a single atom. During the briefest fraction of a second after the Big Bang itself, a leading theoretical framework called cosmic inflation proposes that the universe underwent an extraordinarily rapid period of expansion during that earliest moment, stretching those microscopic quantum fluctuations up to vastly larger, eventually galaxy-sized scales, effectively imprinting the universe's later large-scale structure, including, eventually, the dense gas clouds that would one day collapse into the seeds of black holes like the ones found inside little red dots, directly into the fabric of space itself before the universe was even a full second old. Push the question back any further than that, asking why those particular quantum fluctuations had the particular statistical properties they did, or why the universe underwent inflation at all, or what, if anything, came before that initial moment. And the answer runs directly into the genuine, unresolved boundary of modern physics. General relativity, Einstein's theory of gravity, describes the large-scale behavior of space, time, and matter with extraordinary precision, confirmed repeatedly across more than a century of increasingly sensitive tests. Quantum mechanics describes the behavior of matter and energy at the smallest scales with equally extraordinary precision, underlying nearly all of modern chemistry, electronics, and particle physics. At the conditions believed to have existed during the universe's very first moments, both theories should apply simultaneously, describing an incredibly dense, incredibly small region of space-time. Yet physicists have not yet developed a single, complete, experimentally verified theory that successfully merges general relativity and quantum mechanics together under those extreme conditions. The search for that unified theory, often discussed under names like quantum gravity, remains one of the largest open problems in all of physics. In that sense, little red dots function as a kind of long thread, stretching from a familiar, well-understood phenomenon, observing distant light through a telescope, all the way back to one of the deepest unanswered questions humanity has ever asked. The light-reaching web from Glimpse 17775 left its source roughly 12 billion years ago, long before Earth, the Sun, or the Milky Way's familiar spiral structure had fully formed, and it traveled across an expanding universe, stretched from its original wavelength into the infrared light webs instruments were specifically built to detect, before finally landing on a golden, segmented mirror floating roughly 1,500,000 kilometers from Earth, at a gravitationally stable point called the second Lagrange point, decoded carefully, piece by piece, across years of competing theories and finally confirmed through 40+ individual spectral lines. That light has revealed an entire hidden chapter of cosmic history. Black holes, forming faster and more extremely than anyone expected, wrapped in dense cocoons of their own making, briefly resembling stars before, eventually settling into the more familiar quasars and active galaxies that populate the rest of the universe's long history. What remains genuinely unknown stretches in both directions from this discovery. Looking forward in cosmic time from little red dots, researchers still need to understand exactly how and when each one shed its gas cocoon, and how closely that transition connects to the well-established black hole and galaxy relationships seen throughout the much later universe. Looking backward, past the little red dots themselves, past the first stars, past even the universe's earliest structure formation, lies the genuinely open question of what set the universe's initial conditions in the first place. A question current physics can describe in remarkable mathematical detail right up until the very beginning, and then, at that final boundary, can no longer answer at all. That open question is, in its own way, the most honest place to end this story. Not because it is mysterious for the sake of drama, but because it happens to be true. Astronomers have just resolved a 4-year-old puzzle about strange red dots scattered across the deepest images ever taken of the universe, tracing them back to a specific, well-understood physical mechanism involving black holes, gas, and light. And that same careful, evidence-based process, followed back far enough, arrives honestly and without exaggeration at the genuine edge of what anyone currently knows. If you find that kind of process interesting, watching real scientific mysteries get solved piece by piece, rather than staying mysterious forever, sticking around for whatever gets uncovered next is worth doing, because the universe, it turns out, keeps producing exactly this kind of discovery on a fairly regular basis. What scientists still do not know about little red dots falls into a few clear categories, each one actively being worked on right now rather than sitting unexamined. Whether every member of the catalogued population of 341 objects, and the many more expected to be found by Roman and other future surveys, share the same underlying black hole star structure, or whether some genuinely represent the alternative supermassive primordial star scenario, remains to be tested directly against more individual deep spectra. Which specific seeding mechanism, or combination of mechanisms, actually produced the underlying black hole population in the first place is still constrained more by theoretical plausibility than by direct observational proof. The detailed physics of how and why the gas cocoon eventually clears, transforming a black hole star into a more ordinary, visible quasar, has not yet been observed directly in any single object caught in the act of that transition, and the exact role little red dots played, if any, in reionizing the early universe remains an open, quantitative question rather than a settled one. Each of those questions has a clear observational path toward an eventual answer. More lensed targets studied at the depth of glimpse 17775. Wider surveys from Roman building larger statistical samples. The extremely large telescope reaching fainter, more typical objects without needing a lensing assist, and eventually, if a sufficiently sensitive next-generation X-ray observatory gets built, a direct test of exactly how much X-ray light these objects truly produce at the source. None of that work requires inventing new physics or abandoning any currently well-established theory. It requires exactly what solved this particular piece of the puzzle: patience, better instruments, a fortunate alignment with a massive galaxy cluster's gravity, and researchers willing to spend years checking and rechecking a strange signal until it finally resolves into a clear, well-supported answer. Little red dots were not the only early clue Webb provided about supermassive black holes, existing earlier than expected, and a couple of specific individual discoveries from the years just before the black hole star model solidified are worth mentioning, because they show how this entire research thread built up gradually rather than appearing all at once. In early 2024, a combined analysis using both Webb and the Chandra X-ray Observatory identified an object known as UHC-1, sitting at a redshift of roughly 10.1, corresponding to a time only about 440 million years after the Big Bang. Unlike most little red dots, EOHC-1 did show a faint but measurable X-ray detection, and the inferred black hole mass, somewhere in the range of 10 million to 100 million solar masses, appeared roughly comparable to or even larger than the total stellar mass of its host galaxy, an extreme version of the same overmassive black hole problem seen across the broader little red dot population. UHC-1's discovery, alongside a separate, similarly extreme object identified within the GNZ11 galaxy, first found by Webb in 2022 as one of the most distant galaxies then known and later shown to harbor strong evidence of an actively feeding black hole as well, helped convince much of the research community by mid-2024 that overmassive, early black holes were not an isolated fluke, but a genuine, repeatable pattern showing up across multiple independent objects and multiple independent survey teams. These earlier, individually striking discoveries helped set the stage for the broader, population-level studies that followed. Once researchers had a handful of confirmed examples showing the same basic pattern, severely overmassive black holes relative to tiny host galaxies, appearing within the universe's first 1 billion years, the systematic little red dot catalogs built from CARES, JADES and CosmosWeb data suddenly looked less like a strange, isolated curiosity and more like the visible tip of a much larger, previously hidden population, one that the black hole star model would eventually explain coherently as a class rather than object by object. Considering everything together, the little red dot story spans roughly 4 years from initial puzzlement to a well-supported, multiply-confirmed physical explanation, a relatively fast turnaround by the standards of major astrophysical mysteries, many of which take a decade or longer to resolve, if they ever resolve cleanly at all. That pace reflects both the unusual abundance of these objects, hundreds of independent examples available for study almost immediately, rather than a single rare specimen, and the rapid, often independently converging pace of theoretical and observational work across multiple research groups racing toward the same underlying explanation from several different directions at once. The broader lesson embedded in this particular discovery extends well beyond little red dots themselves. Webb was built, fundamentally, to look further back into cosmic history than any previous telescope, deeper into the era when the universe's first stars, galaxies, and black holes were still forming out of raw, largely unprocessed primordial gas. Finding genuinely unexpected, initially inexplicable objects in that era was always a realistic possibility, arguably one of the strongest justifications for building such an ambitious and expensive instrument in the first place. Little red dots turned out to be exactly that kind of discovery, something nobody specifically predicted. That took years of dedicated effort across multiple research teams to properly understand, and that ultimately revealed a previously unknown stage in how the universe's earliest supermassive black holes actually grow. There is no obvious reason to assume this will be the last such discovery Webb produces. The telescope is still relatively early in its planned operational lifetime, Additional deeply lensed fields remain to be studied in similar detail to Abell S1063, and entire categories of early universe astrophysics, including the still undetected first generation of stars, remain open territory for exactly this kind of patient, methodical, ultimately rewarding investigation. It is worth restating plainly what actually changed between 4 years of genuine puzzlement and the result announced in June of 2026. Nothing about the universe itself changed. The little red dots had always been black holes wrapped in dense gas, every single time Webb photographed one, going all the way back to that very first deep field image in the summer of 2022. What changed was the depth and clarity of the evidence astronomers were able to gather, first through broad statistical patterns across hundreds of objects, then through careful theoretical modeling that proposed a specific physical structure capable of explaining every observed feature at once, then through a mass correction that resolved an apparent conflict with the standard cosmological model, and finally through one extraordinarily fortunate alignment between a distant black hole and a foreground galaxy cluster, magnified just enough to let Webb gather 40+ individual spectral lines instead of the usual handful. Each step narrowed the range of remaining possible explanations a little further, until only one model remained standing against the full weight of the evidence. That is, in the end, a fairly accurate description of how most genuine scientific mysteries eventually get solved. Not through a single dramatic revelation, but through a long, careful accumulation of evidence, repeated independently by different research groups, until the explanation that keeps surviving every new test becomes, for practical purposes, the answer. Little red dots spent for years looking like one of the strangest unsolved puzzles in modern astrophysics. They are now one of the clearer examples of how that kind of puzzle, however strange it looks at first, tends to resolve once enough patient, careful observation gets pointed at it. Whatever Webb photographs next, in whichever deep field comes after this one, will likely follow a similar path, an unexpected signal, a period of competing explanations, and eventually, given enough time and enough light, an answer. For now, the catalogue stands at 341 confirmed little red dots. One of them, Glimpse 17775, understood in far greater detail than any of the others, and the rest waiting for their own lucky alignment, their own 80-hour equivalent spectrum, their own chance to confirm or complicate the picture that one gravitationally magnified object has just made remarkably clear. Somewhere behind one of the many other massive galaxy clusters Webb has already mapped, another deeply lensed little red dot is almost certainly sitting in the data, waiting to be noticed.